All right, so today we're going to talk about the BOOM open-source out-of-order processor. My name is Celio. I built BOOM as part of my PhD project here at Berkeley. I graduated 11 months ago, and now I work at Esperanto, where I get to build superscalar out-of-order cores written in Chisel. Although I've graduated, we're also going to hear later today from a new crop of students that are going to be maintaining and improving BOOM going forward. So this is not a finished project. I think there's going to be a lot of cool things to still do with BOOM. How do I advance? Here we go. So I'm first going to briefly motivate kind of why we did this and why you should be interested. And then we'll do kind of a scattershot overview of the microarchitecture and kind of what's going on. And then I'll hand it over to the new guys to talk about the current state of the project and a little bit more about how to get started, how to contribute, and things that they'll work on and things that you guys can maybe work on. But we're certainly very happy to accept pull requests, improvements, bug reports, and all that good stuff. So we don't want this to just be us doing things and then giving it out to you. So it turns out that modern processors are kind of complicated. There's a lot of stuff going on. I probably don't have to convince you guys of this. But if you're a researcher, you probably want to be playing with something that's somewhat modern. And if you're industry, you want to make sure that maybe you have tools that can actually build something that's modern. Unfortunately, as researchers, single-thread performance is kind of flatlined, or at least at the highest end, it's flatlined. For others of us, we're still expected to somehow give you 30% performance every generation. But that means that we have to have a design methodology that we really trust that the results, the research that we're doing is actually real values. And we also have to be able to measure things like power, area, or timing if we're going to evaluate some of our ideas. Unfortunately, among kind of the academic audience, there's generally been a lack of effort to build and evaluate these out-of-order designs. There's a few great counterexamples. For example, I think MIT just had a paper in Micro a month ago on their BlueSpec out-of-order core. But otherwise, most research is software simulators, and there's a lot of sins of these. A lot of them support an entire full system. You want to be able to run off-the-shelf software running on full operating systems with interesting interactions. You want to be able to get power and area numbers. Even if you use something like McPat, they've been verified against older technologies and older processor designs. And the thing that offends me the most is how slow they are. 10 hours to simulate 1 second of target time just isn't really going to cut it for the modern applications that we actually care about. Even industry design teams keep changing and tweaking, so it's not like we've figured out how to build a processor. We like to change things. It's also, there's no such thing as a good, the best processor. Different form factors require different setups. So I think you've seen Sci-Fi with Rocket Ship and their cores let their customers parameterize all sorts of things. Google talked about yesterday how they had multiple different configurations of their designs. Same thing with superscalar out-of-order high-performance processors. At Berkeley, our approach to research has been, let's just do max fidelity, max effort. Let's give the RTL of an entire processor system so that way we can run real applications on real operating systems. Let's put this on an FPGA so we can run this at 50 to 100 megahertz, and we can actually run now trillions of instructions in only a few hours. And if we actually want power models, we can get that from the RTL. We can get activity factors from the FPGA, and we can build a model, but hopefully a more confident model than what you get out of a software simulator.
Move the mouse.
Move the mouse.
Yeah, there we go.
Oh, and let me know if you guys have questions too. So this can be interactive. So this has kind of been our effort, and we have a few papers on this stuff like Strober and Midas and FireSim. And to motivate some of this, this is Martin Moss collecting really awesome data on Rocket Ship RTL. And he was doing hardware co-simulation of garbage collected languages and a hardware garbage collector. And in this particular case, we were modeling a DRAM memory controller, and we're just measuring the row miss rate of different policies. And it turns out that if you run 2 minutes of Java, stuff happens, and you want to see what's going on. You can't just pull out little snippet checkpoints to run. And you also, you could run on real hardware, but you want to have access to the RTL that you can add in new performance counters that maybe magically read what's going on. And you can get access to this very high fidelity data. So I think this is pretty awesome stuff. And it'd be great to be able to run some of this stuff on Boom as well. So there's a lot of things that you could use Boom for. Some of the ideas that I've been thinking about is you could use this simply as a complex piece of IP that you want to study methodologies for. Either you want to model RTL performance, or how do you model RTL performance before you tape out? How would you model RTL power? Can we use this to prove out an agile verification story? How do we verify complex IP? I think that's an open-ended question. Particularly, can we use Chisel to be a benefit as opposed to a burden here? People that are trying to develop open source CAD flows, this is a good block of IP that you can prove out, something with a lot of highly ported memories. As I showed with the Java stuff, you could use this for hardware software co-design. If you just want to use this as an off-the-shelf core, like FireSim does, or maybe you want to add accelerators, you can maybe memory map those accelerators and talk to the accelerator through that. Or if you want to prove out better implementations of maybe branch predictor and issue queue, you can use that too. And then of course the big one right now is security research. So with Boom, it does speculate. It will speculatively refill your caches. The branch predictor will do things, and the branch predictor state will live across context switches. So you can recreate all of your favorite Spectre attacks. And then you can go and change the RTL to go and then prove that you fixed it somehow. So I think that there's a lot there. So what is Boom? This is our Berkeley Out-of-Order Machine, superscalar, out-of-order. It implements the RV64G RISC-V ISA. That is the general purpose ISA that does not include the compressed extension right now, but it does boot Linux. It's open source. It's about 16,000 lines of Chisel for this core. And it is a parameterizable generator, so you can change things like how many LUs you have, the widths and sizes of different things. And part of what allowed us to be productive is that we built this on top of Rocketship. It's also real, so this is a tape out that we did last year, and I gave a presentation at Hot Chips. The link is provided, but this is a single core talking to L1 and L2 caches that ran at 1 gigahertz at nominal voltage and could run Core Mark and boot Linux and run real applications. So you actually can take this source code and you can take it to a chip that may actually work. Now again, what helped us do this productively was we were able to leverage open source RTL of Rocketship, which started in 2011, and I think now it's been taped out 17 times by Berkeley, and a lot of other times by other people. This is maintained by Sci5. They were the original devs at Berkeley, and then they graduated and started a company. So I can literally say that this is commercial quality RTL for Rocketship. And what we've done here is we take a Rocket tile, and we instead replace that with a Boom tile. But otherwise, we get the coherence manager, the tile link to AXI converters, the boot ROMs, the debug modules, the interrupt stuff. All of that we don't have to deal with. We get to just replace it with a tile that speaks tile link, and then everything else comes for free. And any bug fixes that they do to Rocketship, as that continues to be developed, we get that for free. So this has been a huge productivity win for us, that we can focus just on the core. So this is what the BOOMv2 Core is. I'll explain a little bit more between what, yeah?
Sorry to interrupt. So, talking about consuming those upstream changes, how painful is that? Is it really just a drop-in that you can update your Rocketship stuff and it just works? Or do you have to do refactoring inside your Boom tile? How big of a pain is that in real life?
Yeah, this has taken a while for us to kind of figure out what works and what doesn't work. For a long time, I was a fork of Rocketship, and that would be painful because once you're a fork, you can very easily change something locally and not really think about that as an API, and how that suddenly becomes painful when you have to do a merge conflict. So what we've moved to is, and it was also like, well, I'm only really the core, I'm not the caches. Should the core be the unit that I change things? Should it be the tile? So So what we've decided on is we depend on Rocket Ship master. So we do not fork Rocket Ship. That was such a pain to be a fork of. So we're going to rely as Rocket Ship as a library. We'll use the master copy, and if there is something that we have to change or modify, then we're just going to copy that code into our code base. So for example, the instruction cache or the data caches, we finally had to admit we need to modify them for BOOM's purposes, so we just copy the code into our code base. And that's a little unfortunate. If Sci-Fi improves an iCache, then we have to manually go through and see if there's anything we want to take from that. But we've decided that the tile is the interface. So there's a base tile, and then from there there's this a Rocket tile or a BOOM tile, and both of those can fit into a base tile socket. And that has been a very slow changing interface to talk to the tile. So for us, it's not usually too painful to do these updates, but it took a long time to figure out what the interface should be. And part of it is, and we're not there yet. We treat Rocket Ship as a library, but that means that there's an API, and the API should be slow changing, and we don't have a great way of enforcing that. But they're pretty considerate. They know what we're doing. We talk with them, and sometimes if there's something that we have to fix or change that is something that we use, we'll push that back upstream. So it's been a learning experience, but it helps to be talkative with the other side.
And I think also within the last year, the Rocket Ship changes, integrating them has generally taken less than an hour for pushing forward.
Yeah, it used to be like a week,
yeah.
But it's gotten better. Once we realize what is fast changing, what's slow changing, and then paying the penalty to fix the interface and go forward from there. So this is what at least a version of the core can look like.
I also have
Yeah.
a question. So the thing is that you guys are on, again, an L2 cache, which might not be there. I mean, a cache hierarchy. So does that also tell that you have changed the coherence manager? Because in that figure, it seems that the coherence manager is outside the tile.
Yeah. So.
You guys used.
Yeah, so when we did the BROOM tape out, this was using an older version of the tile link in the Rocket Ship Core. And so there was an open source L2 cache that was a little buggy, and it used older tile link. And so we could do that tape out with open source RTL, but using an older version of the Rocket Ship Core and the Rocket Ship tile link stuff. So that was a little bit of an interesting challenge. I was actually using an up-to-date BOOM source code with an older version of Rocket Ship. We figured out the connection and the parameters system and stuff such that we could actually do that. So that's why we ended up with an L2 for this design. Right now, once Rocket Ship moved to the new tile link implementation and cleaned things up, unfortunately we lost the L2 cache. It had to be rewritten from scratch, and Sci-Fi did that, but it's not yet open source. So unfortunately right now that means that modern, up-to-date, open-source BOOM has private L1 caches that's within the tile. But then once you go outside the tile, you hit this broadcast coherence manager to maintain coherency across these tiles. And then once you're on the back side of the coherence manager, now you're uncached going out to your DRAM. So I don't know what the timeline is at Sci-Fi. Said that they've cleaned up their L2. If someone else wants to write an L2 and provide it back, that'd be great. But right now we only have L1 caches that are cache coherent among each other. So this is our out-of-order core. In the front we have the instruction fetch unit. So we have instruction caches and a branch target buffer that's making predictions without actually seeing the instruction stream. There's also a conditional branch predictor that's making taken or not taken predictions, and it's using data from the instruction cache to decide where the actual branches are and what the targets are, and that'll make redirections. Then it fetches these instructions and puts them into a fetch buffer that allows the front end to run ahead of the back end. And the back end will then decode these instructions and then rename them. We use a physical register file design. So essentially we're renaming from the ISA register specifiers to a physical register specifier. So So these register files will be like 128 registers, even though the ISA may only have 32 integer and 32 float. And once we've renamed the registers, we'll put them into one of three issue queues. So any loads and stores will go to the top queue. Any sort of arithmetic integer operations will go to this middle queue, and all floating point will go to the floating point pipeline. And once operands are ready to be issued, once their operands are ready, they'll request to be issued. We can issue them out of order out of these queues. And then once they've been issued, they'll go to the register file to read out their operands. Then they'll go to execute, and then they'll write back immediately and speculatively. So the register file is holding both speculative and committed data. And something else that's interesting is that the ALU issue queue has 2 issue ports. And I guess the other ones only have 1, at least as I've drawn. And I think that's all I want to say on this. This is just kind of a pitch for Chisel. Is if we look at like the rocket ship source code, the whole repo last I checked was 34,000 lines of code. That's all the utilities. That's anything that's .scala. Whereas the rocket, I think tile itself is 8,000 lines of code. And then for BOOM, last I checked, it was 16,000 lines of code. And then you add that 16 onto rocket ship's 34. So the whole code base is 50,000 lines of code. I don't know of any other open source industry cores to look at. I know that there's the OpenSpark T2, which is a lot of lines of code. Although I have been impressed that some academics have built chips off of this, so it's certainly doable, but I feel like Chisel's a little bit easier to keep the whole code base in your head on. And the CoreMark score, this is the CoreMark score of what we taped out. We were a little bit limited on area, so we did have to cut some stuff back. So it's a generator. This is about this worst performance it's ever been, but it was real. Or it can go up to 5 point something if you give it different branch predictors and better load use latencies and stuff. So you may hear me refer to BOOMv1 or v2 or v3. For a couple of years, I was hacking on BOOM, and I only had access to educational technology libraries, which were not very good. They would kind of tell you if a critical path was really dumb, but otherwise wasn't enough motivation to really radically change the design. But once we started to do an actual tape out, that's when we actually had TSMC 28 nanometer. We had real memory compilers, and that I could finally justify a lot of work to really split up the design. So I added another stage to fetch. I split up the rename. I split up a single monolithic issue queue into separate issue queues, as well as split up the register file. I pipelined the issue and the register read. So there's a lot of changes once I actually had access to technology. And so we called that release BOOMv2. And that thankfully actually only took about 6 weeks of work to do. It turns out if there's a nice enough generator and the code's organized well enough, we could make these changes really pretty rapidly. And then of course there's BOOMv3. This is kind of a tentative work in progress, so I apologize that the code base right now is a bit in flux. So if you want to use something that's stable, I recommend you go to the release tags in the repository, whereas the master branch is where we'll be doing our development work. So the goal for v3 is let's take lessons that we've learned from the tape out, now that we have a bit more time, to fix up critical paths and fix up the IPC issues that we saw, as well as update the latest RISC-V standards. So there's now Priv v111 and user 2.3. We have done those updates. However, RVC is kind of the de facto standard for Unix processors. So if you want to download, is it Fedora or Red Hat?
There's multiple now.
All right. If you download many of the existing Linux packages, they're all compiled for RVC. So that's something that we do want to update to, so that way we can use the standard off-the-shelf packages. There's also the RISC-V memory consistency model has finally been nailed down. So we now have something that we need to chase, which is this weak memory ordering, and we need to order loads to the same address. And that exists right now, except it's low performance, so we have to re-implement this in a way that we're not needlessly rolling back the pipeline. Even though the loads, actually it turns out loads can go out of order to the same address, it's just so long as no one else notices. So we need to re-implement that in a way that's higher performance. And there's also some changes to the front end of the branch prediction units based on what we learned from the tape out. Unfortunately, we have to debug those changes, so that's unfortunately in flux right now. And then one thing that I was pretty happy with is I think originally BOOM was a 3 or 4 cycle load use, and then for the tape out to fix some critical paths, it had to go to a 5 cycle load use. So that's partly where the Cormark score dropped like 20%. But now what we have committed is we speculate that there's going to be a cache hit, and this ends up saving us 2 cycles, as well as it improves the critical path. So that was pretty awesome that everything could just get better. I'll have a slide on that in a bit. Let's see. So this is the current front end. This is a bit different than what the BOOMv2 tape out was. Basically, we're fetching instructions and we're doing the TLB lookup in the same cycle. In fetch 2 is when we'll do the way select, and we can start to decode the instructions to see are there branches, are there jumps, are there returns. If you do RVC implementation, fetch 2 is where you would do the RVC expansion logic. And then in fetch 3 is where we would then put the instruction in the right place to write that into the fetch buffer. And that's step gets more complicated with RVC. From the branch prediction pipeline, this is operating in lockstep with the instruction fetch. So this is I guess a coupled pipeline. And we have a BTB, which also has a return address stack predictor. And this is set associative, partially tagged. So later in the fetch 3 stage, we actually have to check if the BTB made a correct prediction, or if it just predicted complete garbage. And then there's also a bimodal table, which is basically just a table of 2-bit counters, and that helps tell the BTB if you saw a hit, should you actually take it, as well as that can act as a base predictor for the conditional branch predictor pipeline. And so then we have this branch predictor pipeline. For critical path reasons, we give a whole cycle to compute the hash. If you're clever and depending upon your exact technology, you can maybe play games with that. But for us, we're synthesizable, we're a generator, we just give it a whole cycle. And then in fetch 2, we actually access the RAMs. And then in fetch 3, we actually know where the branches are, and we know where their targets are. And then we can make a decision based on what the branch predictor said, what we should do. And then in fetch 4 is when we actually do a redirect. So if the BTB wants to make a prediction, there's going to be a one bubble. There's going to insert one bubble in the pipeline. So it's I guess a 1-cycle predictor. And if our conditional predictor makes a prediction, there's going to be 3 bubbles in the pipeline. So the idea here is that you'll run your instruction fetch at say twice the width of the back end. So that way, you don't always have branches. They're not always taken branches. And if you run it twice the width, it turns out this actually kind of matches the bandwidth of the back end. So this ends up not being a big deal to have a 3-cycle bubble on predictions. The other thing I wanted to mention is this is a change from V2 to V3. There's now a fetch target queue. So basically, if you're familiar with out-of-order processors, you have a reorder buffer, which is kind of storing the PCs and the instructions and the rename logic and who's had an exception or anything. And it turns out most of that actually just kind of disappears. You don't need any of it. And in this case, almost all of that logic has been moved to the FTQ. So this stores 1 entry is for every fetch cycle, and we store the PC that was at the beginning of the fetch, and we also store the branch prediction information for that fetch cycle. So we enqueue to this in the front end, and then the back end will tell us when we've committed an instruction, and we'll deallocate entries from the FTQ, and then we'll update the predictors. So I think in the past I called it the branch ROB, but now I just call it the FTQ. And it turns out that the backend now no longer has to see PCs, which saves a lot of space and complexity. One of the things that I played around with was branch predictors, and trying to use Chisel and object-oriented programming to describe branch predictors kind of in a nicer way. So we have some sort of pipeline, and I apologize if this diagram is for BOOMv2. But the idea is that a lot of branch predictors are going to have things like a global history. They're going to have things like they need to store these predictions, and they need to be given whatever they had read later to do the update. And so there's a lot of infrastructure that make a branch predictor really complicated. And so it was nice to just put that into a base class, or I guess you could say like the super class of a branch predictor, a generic global history branch predictor. And then if you want to come in, you want to implement gshare, or you want to implement Tage, or maybe a neural net predictor, you just have to come into this red box and you just implement the hash function, given some global history that was given to you from on high, and the PC, you give the hash function, and then you'll give the table organization for, again, I apologize, the pipeline's been moved back a stage, but you'll just say, here's the tables, and here's how they're read and indexed, and then you'll give out a bit vector of here are my predictions. And so this allowed me to implement and play around with different branch predictors while not having to touch the really not very fun code of having to actually update these and having to manage the global history and all that stuff. So this is a nice part where kind of object-oriented programming in Chisel was a really, really nice feature for me. And you can still do clever things like a single-ported gshare predictor and all that good fun stuff. Let's see. So this is the 4-cycle load use pipeline that I changed recently. So you issue instructions, or I guess instructions get woken up in this issue queue. They request to be selected. Then on the next cycle, they'll read the register file, and if their data is not there, they'll get the data out of the bypass network, and then they'll go and execute. And if it's ALUs, those can be executed back to back because we'll bypass behind themselves. But if it's a load instruction, what we're going to do is once the load hits the memory stage, we're going to wake up everyone that depends on this load. And then on the next cycle, we're going to hit a new stage that I've added called sign extension. So this fixes the worst critical path in the BROOM tape out after physical design was getting data back from the data cache to the register file. So I've added another stage. And what's nice is we know at the very beginning of the stage that we actually had a miss in the data cache. So we woke everyone up on the previous cycle, and now while we're in sign extend, they're trying to select. And we can tell them, hey, I know you want to actually issue, but don't issue. And so we can actually stop microops from leaving the issue queue. So that's kind of nice that we don't have to deal with any of this complexity of having to kill we're trying to kill the children, but we're not trying to kill the grandchildren, and that becomes a huge mess in these pipelines. So we can squash updates in the sign extension stage, and if it was a hit, and write back, we're going to line up with the child hitting the register read stage, so we can actually get it out of the bypass network. So this was awesome because it fixed the worst critical path by adding a stage. It was actually pretty simple implementation because you're only having to kill children and not grandchildren, and it actually shaved the cycle off of the load use delay. So this was a really nice new addition. We have an execution pipeline generator that's pretty clever and complicated, but the nice thing is that you can add, say, additional LUs or add more stuff, and the bypass network is auto-generated. The read ports and the write ports are auto-generated. What I will say here is we only support one load or store a cycle, so that would be a performance bottleneck. And we also don't do any clever read port sharing or write port arbitration. So whatever you ask for, the maximal is the maximum number of read ports and write ports that you're going to get. And I think the other thing I wanted to say for the code base is the way that we handle branches is the MIPS-R10K style. So every branch is allocated a rename snapshot of the rename tables, and every micro-op that follows that branch will have a bit set and a branch mask that goes down the pipeline. And that allows us, if a branch is mispredicted, we can broadcast to the whole machine, this branch failed, and if you have that bit set, then you can gracefully leave the machine. And if you were correctly predicted, then they just clear the bit so we can reallocate it. So this is a little expensive, but not as bad as I thought. And it turns out this makes things really easy because there should be no micro-ops that are in the machine after one cycle. So this was a help for verification. I think I'll skip through most things and say that, like I said, this is a real thing. So we did have to deal with issues like physical design, things like trying to get a register file to place en route. If you give it enough area, maybe it'll be okay. In our case, what we did is we did black box the register file and manually instantiated, or I guess kind of by hand instantiated cells from the cell library to describe a unit, like a bit in the register file, and then we could replicate these unit cells. So that was that worked out pretty well in terms of being able to be DRC clean, LVS sane. But maybe you can get away with fully synthesizing, but sometimes you want to play around with either actual physical design or just power numbers. The register file is one place that you may have to do some a little bit of custom work on. But I think everything else we otherwise just synthesized. I don't think there's anything else that we black boxed. Verification is an ongoing story. We use Torture Tester. We use Verilator a lot, sometimes VCS, maybe to get waveforms out. Turns out speculative out-of-order pipelines are really kind of hard to get coverage on, and it's hard for torture testers to hit them very well. So we rely on assertions in the source code. And I think we're in progress to moving towards a co-simulation environment so we can really test against an ISA simulator, because that'll catch a lot of bugs. If you want to use the code, you can go to github.com/riscv-boom. Also, I recommend checking out IntelliJ. The BOOM template README gives some advice on how to set that up. If you saw Henry's thing in the previous session about Rocket Ship, there's a lot of code. There's a lot of library stuff going on, so IntelliJ is very nice for helping bounce you around the code base. And the way that we set up the repos, we have this thing that we call the template, and that as submodules calls in Rocket Ship as a library and riscv-boom as the actual source code. And this template is just kind of gluing together the SOC. The main source code lies in BOOM though, and then Rocket Ship is our library. So one thing you can do is when you do a tape out or you go to an FPGA or you do something interesting is you just kind of fork the template and you can then start to specialize your SOC for your particular thing. I think my last slide is, here's kind of the hierarchy of the tile. So right now the way that it's organized is we have the data cache, we have an instruction fetch unit with an iCache, and they share a crossbar to go out. And then we have this out-of-order core, which is BOOM. And I think, so in terms of source code that came from Rocket, the data cache came from Rocket, the iCache, the TLB, the page table walker, crossbar, all of that collateral came from Rocket Ship. Although I think by now we've kind of hard forked these into the BOOM repo because we have to start kind of customizing them a little bit for our purposes. So what we provide to Rocket Ship is this BOOM tile, and that's what we actually glue in. The page table walker at TLB stuff, we still instantiate that from the library, but this is kind of the current setup of a tile. I think with that, I'll, any questions before I hand it over?
So how was you said that you repipelined because of actually having a real library.
Yeah.
And how did that work out for you in Chisel? Because some of the talk yesterday was about change one minor thing in Chisel, and then I get a wildly different, parallel code base. And if you're trying to, control repipeline to fix some critical path, often that can get into a frustrating situation.
So yeah, so this was trivial. I literally just said add a register, and it just worked. Now I'm lucky because some of the wake-up logic gets registered, and so that just kind of comes for free. I had to think very, very hard about this, child wake-up, grandchildren problem, and if I didn't have this stage, you could see how once you really start having these really tight loops and these feedback things, and you want to change the logic a little bit, think very hard. In this case, just trying to basically just buffer the write back another stage, that ended up being really easy, and I just kind of got lucky. Another thing I did is I added, I was originally doing redirection on F3, and that was a critical path for synthesis. And so for me, it was actually trivial to add another stage here, and then the redirection just comes a cycle later. Now, I don't have a validation team breathing down my throat about the coverage report just got all foobar. But from a functional point of view, it was really pretty easy to make these. The BTB doesn't change, the conditional predictor doesn't really change. I'm just kind of taking these blocks and changing the registers around and kind of the organization around a little bit. So I could actually do that pretty fast and kind of retime things pretty fast. But I wasn't having to worry about coverage reports or how much, this completely undoes the verification effort. It's like kind of start over again.
Right.
But it's a new design. So that ended up not being too bad. And then the rename stage, that one was a little painful because there's a lot of back pressure. Which one is it? Having to split up rename across 2 cycles was a little bit more painful. When I say painful, it was like 2 weeks of effort. But that's because there's a lot of back pressure in these queues, there's back pressure to the ROB, and so the fact that now rename could stall in 2 cycles, that made that a little bit harder. But in terms of effort, repipeline things I didn't find was too painful.
Yes, I also had kind of the similar question that once you have this, let's say a branch predictor block and you want to change it, and that just completely pipelines the design.
Mm-hmm.
So how difficult was that? So in the same way, like since this is like it looks like it's super custom. So if you want to change, like add new instructions or change the number of bits of the ISA, I mean, how flexible is it? Because this can support 32-bit, 64-bit, and
yeah. So this only does 64-bit. 32 would probably maybe not be that hard. At least most code is written to just say excellent, and then you'd have to make sure, maybe modify the physical register file. And I think it's mostly just changing the LUs to understand the different semantics of 32-bit. That one's probably not too bad. But yeah. Guys ready?
Sure. It's just like that.
This is the next one.
Yeah. All right, so thanks, Chris. So now we're going to move to the second section of this intensive, where we're going to talk more about sort of work that we see going forward will happen to BOOM. All right, so starting off, Chris is now not with us, but we at Berkeley are still very committed to continuing to not only maintain the project for our own research, but also make it more open and accessible to community members who want to use this project. And so I'm Jerry, and with me is Ben and Abe here. So just briefly summarizing some of the recent and ongoing work that's been happening to BOOM. Chris mentioned he taped this out as the BROOM chip, so it's verified and reasonably validated. A lot of the work that's happened over the past couple months is integration of BOOM with the FireSim project. So if you haven't heard about FireSim, I highly recommend you go to the next architecture intensive. They're going to talk all about this. But to briefly summarize, it's an open source FPGA acceleration framework that leverages F1 FPGA instances on Amazon EC2. So what this lets us do is it lets us configure and build really complex simulations like multi-core, multi-node BOOM simulations with realistically simulated DRAM, block devices, peripherals, network models. And let's just run these simulations in the cloud at reasonable performance and very cheaply, since we don't have to pay the upfront cost to buy the FPGAs. And I think in the next talk, I highly recommend you go to the next intensive on this, because you'll learn how to very quickly set up your own simulation and run BOOM on FPGAs. And so the rest of this talk, or this intensive, is going to be mostly talking about work which we're doing towards the BOOMv3 release and some of the interesting research directions we want to pursue as well.
So for a lot of people, it's probably their first time working with the BROOM repo. So there's a little bit of stuff to get people up to speed. So we did a major overhaul of the organization of the repo and how everything works within it. So the first thing is now there's a website where you can get access to all the information that you might need. This includes documentation, who's working on it, links to different talks such as this one that's going to be posted up soon. It is the end-all and be-all of all information that you might need outside of the source code that is located on the GitHub repo. So specifically with the GitHub organization, as Chris mentioned, you're going to be able to find the BOOM template there. So this is where we're going to be working on both the core and the template. Within the core itself, you're going to have all the source code and links out to Rocketship. And then there's also documentation up here. So if you want to make some changes to the documentation and make it more accessible to everyone, you can go ahead and add it there. Specifically with the documentation, so this is probably the best way to get started with the code base outside of looking at the source. So you have many, many pages of documentation on the different stages of the core itself. And then you also have little tidbits on what the layout is, what's reused from Rocketship, some of the verification that was done, some of the different tools that you can use to debug the core itself. So this is a great way to get started and to read through it. However, one thing is that this is not exactly up to date. It's mainly up to date, but there's a couple changes that need to be done to keep it in line with the current source code. So one of the main points that we're looking to do for BOOMv3 is to make sure that the documentation is up to date.
So I'm going to quickly touch on how you can contribute to Boom. So bug reports are always greatly appreciated. So say you have some piece of code that appears to be misbehaving on Boom. What you might want to do first is verify that it is actually a bug with Boom and not the code by running it on the Spike ISA simulator. And then after that, you can add an issue with a reproducible snippets of code that encapsulate the problem. And then that way people can run it on Boom, try and debug it themselves. And if you're thinking of wanting to add a feature or wanting to fix something, if it's major, you're going to want to definitely be reaching out to us to discuss it. That way we can collaborate and we can avoid conflicting work, conflicting features that are going to break each other, and we can just generally bounce more ideas around that way. But feel free to do whatever you want on your own private branch, of course. This is about going into master. And after you've implemented a feature, you're going to want to submit a pull request with a detailed description of what you've changed. And don't forget to do documentation update alongside your code updates.
All right, so now shifting gears a little bit, here's some of the things that we're going to provide a list of some of the things which we are interested in working on. So this list is by no means comprehensive. We try to identify features which we think would be useful for both our own research and might make Boom more accessible or extensible to the community. So starting off, this is kind of low-hanging fruit, but support the ROC interface. So ROC is the Rocket Custom Coprocessor interface. It's a semi-defined interface describing how a RISC-V core can execute custom instructions by sending them to some other module or accelerator. So examples of modules which have been implemented using this interface include the Plocha Vector Accelerator. We have various crypto accelerators, DMA engines. And I think the community has implemented a couple like neural network accelerators, DSP accelerators using this interface as well. And we would really like to see Boom be able to support these accelerators. The problem is that ROC is really designed as an in-order interface, receiving instructions in order. And there are some design challenges implementing it in an out-of-order machine. So in the most naive implementation we can think of, where we just stall the machine and wait for the ROC instructions to commit before dispatching them, this obviously has a lot of performance implications for certain applications. So if this is something which seems interesting to you, we'd really like to hear about it and see what are your requirements for this sort of extensible interface. It might turn out we need to extend ROC to support executing speculative custom instructions as well. So we really like to hear more from you on this feature.
So there's some changes to be done with Boom's memory pipeline. So first of all, over the last year, RISC-V has converged on a weak memory ordering model with an optional total store ordering extension. But Boom currently implements an outdated memory model. So we need to support it to at least update WMO properly. And that'll mean, as Chris mentioned, ordering loads to the same address, which it does do, but in a very inefficient manner wherein conflicts will result in the entire pipeline being flushed. So there's work to be done there. We definitely want to look at adding prefetchers at some point, both data and instruction. Memory disambiguation predictor might be useful. And this plays into what I've mentioned about conflicts to the same address. So this would aim to proactively detect these conflicts before the addresses are actually resolved, and that way we can avoid unnecessary flushes to the pipeline. And finally, a multi-ported data cache would be quite useful, especially for trying to build wider versions of Boom. Because so far, for the most part, implementations of Boom that have been looked at are kind of 2 to 4 wide, but as the width of the machine increases, we would want to be able to perhaps complete 2 cache accesses per cycle. And another thing, as Chris mentioned, BOOM does not currently support the RISC-V compressed instruction spec. And this is very useful. It saves instruction bandwidth, and it's quite commonly used. And so this requires a number of changes to the pipeline. So for example, jump and link will return either PC plus 2 or PC plus 4, depending on whether that instruction itself was compressed. So we need to be able to track whether an instruction was compressed throughout the pipeline. And this is going to require code changes to a number of key structures. So for example, the reorder buffer, it's actually going to more accurately be the FDQ now, but we store the PC alongside a fetch packet. So the majority of the bits of the PC are factored out, and just the lower bits are stored for each instruction for disambiguating which one it was. But with compressed instructions, we may need to be able to store the same factored out PC for 2 fetch packets in a row, and then store offsets on the granularity of 16 bits. And more complicated than that will be changes to the branch predictor.
So in general, we're talking about a lot of different features that we would like to implement, but there's a lot of current work that needs to be done on verifying all the different parts of the processor. So one of the things is we have peak post testers built in Chisel, and we also have rocket chip unit tests. So starting to use those a little bit more to verify all the individual submodules would be great, because more tests is always better. Another thing that we're looking to add that Chris mentioned was this co-simulation against an ISA simulator, so that we can compare this against maybe Spike and then check any outstanding bugs that way. A couple of particular things that we would like to verify is specifically the branch prediction. So there's a little bit of wonkiness inside of the branch predictor that we would like to get fixed up. And then we also want to make sure that we're spec compliant. So these are kind of the main verification things that we're looking for. Additional, just general maintenance, it's always good to have documentation. Source code documentation is not enough. So we're looking to update the documentation to what the source code currently is, transition to read the docs so that it's not only easier to read, but whenever there's a source code change, you can align it to a documentation change. Finally, we already made steps to have a centralized GitHub organization. So now you should be able to find everything there that you might need to work on the project. And then we're looking to do some minor refactoring work around the repo to make it easier for others to work on.
So I'm going to quickly touch on BOOM's role in enabling microarchitectural research. So just in general, the Chisel and RISC-V ecosystem really enables agile architecture research. So we don't just need to settle on modeling. We can build and evaluate fully functional systems. And BOOM itself is a very important piece of groundwork because we can leverage it to actually research high-performance microarchitecture. And it's on the order of 10,000 lines of concise and fairly well-partitioned code, so it is feasible for one person to implement meaningful features. And a current idea that something I've been starting to work on here as a new student is a ring scalar style integer execution core, which is, it's based on a paper done by Kirsta and one of his students back at MIT. And it essentially allows for a wide several of the key structures in a wide machine in the execution backend to scale with the number of, with the dispatch width as opposed to the dispatch width squared, which is quite common. And also, Jerry has been working on supporting the RISC-V vector extension.
Okay, so the other big research target we want to look at is hardware security. So, recently the revelation of Spectre-style attacks is that a lot of performance techniques, to get more speculation out of a core, these are revealing side channels which an attacker can use to learn information about the victim code. So good news first, we're not really vulnerable to Malcolm or Foreshadow, but this actually really isn't news to us because those are already implementation-specific vulnerabilities. We're actually more concerned about the general field of Spectre-style attacks, so general speculative out-of-order execution attacks. And the bad news is we are vulnerable to these. We have demonstrated code that runs on BOOM and can extract information from a victim process. But we consider this to be actually good news because if these attacks didn't work, it would mean that there's either some bug with the core or we aren't understanding it. And since we want BOOM to serve as a baseline for security research, we need these attacks to work here. So the reason BOOM is valuable as a baseline here is because You can leverage the existence of a general sort of base implementation of out-of-order core. You can leverage the productivity and ecosystem of Chisel and Rocketship to, in a very agile fashion, test and implement different proposed mitigations to these speculative attacks. So things like secure caches, cache partitioning, timing obfuscation. It's really fast and easy to implement them and evaluate their effects on performance, cost, and security. So I think Ben, Abe, and I have been working on something over the past few months. Like a really simple mitigation strategy is to block transient cache refills from touching the L1 data cache. So this would essentially mitigate the most basic Spectre v1 attacks. And it took us just 1 man week of work to write the RTL in Chisel and get it reasonably verified and have it functioning, and also verify it running some test benchmarks. And before we finish up, I also like to mention that if you've been following the RISC-V security work, it turns out open source and secure enclaves, secure software enclaves are a really good idea. And since we want Boom to be a totally compliant RISC-V core, we do want to eventually support these enclaves and guarantee their security as well. Question? Yeah.
Does PMP now work for Boom?
We fixed it recently, and we are in the process of verifying it. Yeah.
Whoops.
So it does currently work.
Yeah. It'll be pushed out soon.
I don't think they were very interesting, so I disconnected them. Turns out they're kind of a big deal.
I think they were connected but broken, which might be worse. But so anyways, those are sort of a summary of the directions we want to go in with Boom. Just in conclusion, Chris has left us with this really awesome framework for exploring out-of-order microarchitectures. It's concisely expressed in Chisel. We can do really interesting microarchitectural exploration. And we do want, and since it's open source and extensible, I think we think it's very valuable to the community to have this as well. And we are really looking forward to building more community involvement with the Boom project. So not just us working on it, but seeing what other people want to do with the Boom core. So what we really want to know is what features are you looking for in Boom? What do you need from us in order to use Boom? Is there anything which you think is missing that is blocking you from using it? Yeah, so if there's any opinions here, we are more than happy to hear them. I think at this point, just take questions.
I guess like one question that I think that I'm interested in is, are you like planning to do regular tape-ins for Boom? Like, are you trying to like actually use feedback from going down to a technology?
Yeah, like going through Hammer and
Hammer.
Yeah.
I think that's going to get started up. I think there was a discussion with Adam about kind of going through the Hammer flow.
Okay.
But right now it's kind of in the grumbling stages where it's like starting up.
We want to get some of this microarchitectural work first and get that done out of the way.
Do you have like a base frequency that you're trying to hit? Or is it just kind of whatever you can get?
Yeah.
Whatever we can get at this point.
The gigahertz is kind of the baseline.
Yeah, like we have a baseline with BROOM. So.
I mean, I think I'm pretty happy with the pipeline organization. I've learned through the tape out where critical paths are, and I've talked to other people to figure out what the organization kind of should be. And so I think it's pretty standard with what 1.5 to 2.5 gigahertz cores looks like.
Right.
Obviously it's nice to go through flows to make sure that we don't add a critical path, try and add a speculation refill buffer or something. But I don't think, I think once they have the motivation like a tape out, they can fix those. But I think that they're not going to be surprised and have to add new stages, along the issue queue or something.
Well, I guess what I'm more interested in is like, if we were going to adopt Chisel at Samsung, right? One of the great anxieties we might have is that if we're trying to meet some tighter frequency than what you're trying to meet, and we're fighting with the language, it would be nice to have some experience of trying to eke out as much as possible, like pick a critical path, try to improve it by 50% or something like that, which often happens in the late stages of a project, just to see what kind of experience, whether something that's not in Chisel today needs to be there to help you, I guess. The repipelining thing, it sounds like you didn't have to refactor a bunch of stuff, but if you have to duplicate things and basically redo the way a pipeline stage is done to make 1.5 gigahertz if you wanted to or something.
Yeah, I don't think anything was magical. I want to say post synthesis it was maybe high 30 FF4. NOR gates or inverters. And then place and route was not great because it was too small. It was like 55 FO4 on the cache return path. But it's like if there was a critical path, usually it was I did something dumb and I just had to like move. Like I was just trying to be too aggressive. It's like on the branch kill. You're telling the whole machine kill the branch, and it turns out let's just add a flop, and then I'm done. But otherwise it felt like nothing different between Chisel and having to do this in Verilog.
Okay.
Like I need to move the logic from this side to this side, or I need to just reorganize, pipeline. I didn't feel that it hurt me or that it helped me a whole lot, other than there was just fewer wires. Like everything's in bundles, so there's fewer wires for me to have to deal with. So maybe it was easier for me to reorganize, or maybe the object-oriented of the modules made it easier to move things around. But I don't know that was, twice as better than if it had been in Verilog or something.
Right.
But it didn't feel worse. but it didn't feel magical.
Okay. It's hard to feel worse. But
I have a question about how you handle community contributions. Like, let's say I made I added a feature and sent a pull request. So how do you actually go and verify that it's actually working? And I mean, how do I do that? So you have this FireSim framework, right?
Yeah, so the FireSim framework is all open source. So you could, if you made your own RTL modifications, you could load that into FireSim, and the framework gives you a way to build an FPGA image and launch it, and then run whatever tests you want on it as well.
So yeah, I mean, is there a suite of tests which you want someone to run, or would you do that?
Yeah, so in the repository, in the README, it'll say if you want to build a Verilator simulator, go to this directory, type make run, and that'll build a Verilator simulation, and that'll run it through the upstreamed RISC-V-tests repository, and that's about 200 assembly-directed tests and about 5 or 6 C-compiled tests, and those are self-checking tests. And so that's what we use to kind of gate off commits, is can you run the regressions or not? And that catches a heck of a lot of stuff, but it is also very thin.
Yeah.
But it's probably good enough, at least for what we do. There's the longer stuff of running Torture. There's the longer stuff of putting it onto FireSim and verifying that works.
So do you regularly run regressions? Like, let's say I sent in a PR, you merged it. So do you run regressions at a later point to ensure that it's not broken after a while?
Before every release, we definitely want to make sure boots Linux and gets through everything, right?
I know we've had Jenkins at Berkeley, and we should maybe more automate that or something.
We looked
it keeps getting bit rotted, and then we ignore it, or we don't get the emails. And
so the reason I ask is I tried doing something with FireSim, but it's a painful process. Like riscv-boom currently doesn't support RVC, and FireSim is, I think, more oriented towards that. You have to, you can't compile binaries to run in Boom because the FireSim toolchain doesn't support RVC right now.
I think they've made changes to support it more easily now. So I think it might all be RB64G without C.
Yeah, I think in the last 2 months they have moved to toolchain to doing RPG.
Yeah.
But yeah, right now it's a relatively thin set of scripts. And I don't know that I guess maybe now we can set up Travis. Travis is good, but it's also a pain. But that we could maybe try to use. It's just the runtime is the issue with Travis. But yeah, at least do make run. And when I get patches, like I will run them. I'll make sure that I can run them locally through make run as well. But there's otherwise not a huge flow of verification collateral yet.